Hi, all. Welcome back. Start 9.3. This is our last section. As I look at it, I think I mentioned test next week. Still possible, but it probably wouldn't be on Tuesday, if at all. As I look at this again, this is pretty, there's a lot of different elements that go to this, and I just want to make sure with the guidance they've given us that I do teach you enough, because I'm not exactly sure how much of this we need. So we'll go through this a few days, and then at some point we'll have a test here before we wrap up, possibly next week. I'll let you know on Tuesday. So what you'll see at the top, it's called a power series. Power series, what we've been dealing with is infinite series. It's still going to be an infinite series, but if you look at what this is telling you now, it's an infinite polynomial, so it's not just the sum of numbers. So power series refers to, whenever you hear that, is an infinite polynomial. So you're going to still see, here's our starting integer value. We're going to go on forever. This is now our general term. C sub n is our constant. X sub n would be the variable part of this. So as we kind of look and see how this would be figured, if I let n be a 0, I'd get C sub 0, and then x to the 0 would just be a 1. If n is a 1, I get C sub 1, x to the 1, C sub 2, x2, so on and so forth. When we see this, this is what we would call power series centered at 0, because for each one of these, notice how we have an x, but the reason we don't really have anything, it's x minus 0 to the 0. The reason you don't see anything with your x is because they are all what we call centered at 0. I don't expect you to really fully understand that right now, but just know it's kind of like shifts in some ways, where you have a bunch of zeros here, and that's why you're only seeing an x squared. The next would be x cubed, because we're just doing everything around the value of 0. If we look at this one, and it's written in this way, here's our 0, still an infinite series, constant, variable term. Looks the same. C sub 0, and then C sub 1, this has a power of 1. C sub 2, this is a power of 2. So on and so forth. This is still a power series. It's still our infinite polynomial. But the fact that you have x minus a tells you that we are now centered at a. And again, I don't necessarily expect you to fully understand that just yet, but just kind of relate that back to some things you've done with shifts, parabolas, absolute value graphs, so on and so forth. Next, it says using this series, you have your sum starting at n equals 0, going to infinity. This is our general term. So if you let n be a 0, you get x to the 0. X to the 0 is going to give you that 1. Let n be a 1, you're going to get x to the first. If n is 2, you'll get x squared, x cubed, x to the fourth, x to the n, so on and so forth. Then what I'm asking you to do, so if you have your calculator, you can do it yourself. I'm going to pull mine up here so you can look at mine. But what I'm going to have you do, it says graph the first 3 terms, 4 terms, and then 5 terms. I'm going to do them all when I show you here in a minute. We're going to do a window of a minimum x at -2 and a maximum x of a +2. I want you to graph all those. And then what we're going to be looking at is between a -1 and 1. So our window is going to be -2 to 2. So just inside of that window between a -1 and 1, what's happening when we graph all of those? And this is what we are going to graph. So I'm going to graph the first term, then the second term, third term, fourth term. We're going to go through that process. So let me pull up the calculator. Let me make sure my window is correct. I'm going to make my y's 5. So the first one, if I were to graph 1, we all know what that looks like. It's going to be a horizontal line through 1. Let me see if I can make this a little bit bigger. There, now you can see the whole calculator. So that's our first sum. So that's basically just us graphing just this. So the next one I'm going to graph is 1 plus x, the first 2 terms. So I'm going to do that underneath y sub 2. So I'm going to have 1 plus x. We would graph that. Notice how they intersect at 0. If you think back to what I talked about in terms of where we centered at, this is centered at 0 because you don't, in none of these terms do you see x minus 2 squared, x minus 2 cubed, anything like that. And the reason we don't is because we're centered at 0. So what that would tell us, one of the things it's going to tell us is we're going to go through the x. They're going to all have the same value at the x value of 0. So all of them should be going through that 1. So keep that in mind. The third one I'm going to now graph is going to be all of these 3, 1 plus x squared. Let me do that. Let me graph that. Notice how they go through the same point at 0, 0, 1. Then I'm going to do one more, or a couple more. So let's go 1 plus x plus, oops, plus x, nope. Bear with me here. X squared plus x to the third. All right, so that's our next one. I think I wanted to go through a few more, so let me go down here. Graph that. And then one more final one here. That's all of them put in there. Graph that one. And we should look like that. So what I want you to ask yourselves as we're looking at this, one of the questions was in between a negative 1 and 1. So if you look at, I don't think, yeah, my pencil won't work here. So you have to visually look between the x value of a negative 1 and the x value of a positive 1. The question is asking you what's happening in between there. So if we go back to our document, what we would say in terms of what's happening between a negative 1 and a positive 1, what should visually look like is they're all kind of starting to look like each other a little bit. They're all getting sandwiched on top of each other. What we are writing here is they converge. So what happens on the interval of negative 1 to 1? All the graphs, suppose I could add that. All the graphs are converging upon each other. They all go through 0, 1. They all kind of start looking like the same graph to some extent, but they're all converging within that interval here. I then ask you, what is the sum of this series? So think back, the sum of a geometric series is a sub 1 over 1 minus r. The reason I bring this up, if we go back and look at the series that we're talking about, it is a geometric series. Even though we have variables involved, the way I'm going from 1 to x squared to x cubed to x to the fourth is we are multiplying by a common ratio of x. So if we just use our little formula that we've used now for a little while, a sub 1 means what's the first term? That's 1. We just look up here, it's a 1. And then we would do 1 minus our common ratio. Well, our common ratio is x. We're multiplying by x over and over and over again. So the sum of that geometric series is this function, 1 over 1 minus x. What I now want you to do, and I'll show you, I want to go graph the equation for that sum. So we'll go back to our calculator and do that. So if you see there, I have that entered. If we now go ahead and graph this, don't pay attention to what happened in the bottom right-hand corner, but look at that dark red one that came in. Notice how that red one started to converge upon all those different graphs. What I want you to pay attention to, so now let me see if you can do this. When we just had this one term, so look at y sub 1 equals a1. When we just had that, it was a horizontal line. It didn't really reflect that sum, the function that we said was the sum, very well. Let me clear these out. But the more and more terms we added, so let's go with this one. So look at the horizontal line. The horizontal line, the blue one, doesn't look like the function itself. But doesn't the green one and the yellow one look like that function? So what this is doing, the more and more terms that we include in our polynomial, the more and more and more we are basically duplicating So the more and more of these we add, the more and more closely we are creating this function. When we just put the 1 term in, so we just use a 1, it doesn't really look like that function. When we did 1 plus x, a little bit more. But when we really start adding up more and more and more and more terms, so if I were to actually go back to my calculator and enter into here a 5th one, or another one where I'm going to add this, look underneath y sub 8, I've now added another term. What this should do is make even more of the function that we found to be our sum. It's going to create even more of that. It's going to reproduce a clone of that even more so than the ones before it. So if I graph it, here comes this new one. And notice how that blue one that we just drew in and then the red one, we really can't even tell the difference between them. The blue one overlaps those guys. So the more and more terms, what we want to get out of this, the more and more terms we include, let me erase this. The more and more terms we include in our polynomial here, so if I just continue to add them, the more and more accurately it's going to produce its series. That's what we just found when we graphed it. So when it says what happens between a -1 and a +1, our polynomial produces, let's do it that way, 1 over 1 minus x, the sum of the series. The reason we have to stay between a -1 and a 1, and this is something that we, under normal years, would do this pretty extensively, is think about if this is a geometric series, in order for a geometric series to converge, our ratio has to have an absolute value less than 1. Well, our ratio in this problem is the x, so the absolute value of x is less than a 1. If we solve that inequality, we are going to only converge between a -1 and 1. So once we get outside of that interval, the graphs start kind of doing all their own things. They start going off in all different directions. But as long as we stay in this interval here, those polynomial terms will produce a clone of this graph with the more and more that we add in there. Okay, hopefully that makes some sense. This is, typically something that people start asking questions about that we explore a little bit deeper. So if there's anything, again, you're free to reach out to me at any point in time. So the next set of problems, I'm going to have you find a power series. I want you to do this with an initial term of 1 that represent the following functions. So this is going to be based off of what we did above, that a power series is just a geometric series that, in this case, for what we're going to be doing, multiplying by a common ratio. So if we look at this problem here, we already have a 1 in our numerator. So what that tells us is this is taken care of. And then this should be 1 minus r. Well, look at what we have. We have 1 plus x. So what that would have to tell us is we would have had 1 minus a negative x. So our r in this case had to have been a negative x. So think about what that would mean in terms of a series. First term would have been a 1. We're multiplying by a negative x every time. So the next term would be a negative x, and then plus an x squared, minus an x cubed, plus an x to the 4th, so on and so forth. When you are asked to find a series, we don't just want the polynomial terms. We want to come up with everything, the general term, and the general term will give us everything. So if we wanted the actual series for this, we want to write the general term. So do ... Hopefully you have some room. I wrote that a little too largely. What's happening is this is alternating. So we're going to do a -1 to the n, or n, n plus 1, depending on if you're going to say you start at 0 or n. And then we would have x to the n. So for me, that would mean I'm starting at 0 to infinity. That would be my series. If I plug in a 0, I'm going to get a 1, 1, so that gives me the first term. If I plug in a 1, I get a -1, x to the first, which is our second term. This is our series for this. The other way that we could have done this, which we might want to rely on for some of these here coming up, so if you didn't understand where I came up with that, the other way we can do this is if we want our first term to be 1, we just really need to figure out what's our ratio. Just set that equal to the function that you were given to work with. Solve this equation. So cross multiply subtract our 1s, those would cancel from each side, so we would have gotten r, or x equals a negative r, and then that would tell us that r equals a negative x. That's probably the method we want to use in number 2, because if you'll notice our first term, if we just assume that was our first term would have ended up being a 1. So what we're going to do is take that function and set it equal to what we know we want. So we're really just using this formula for a geometric series. But for our purposes, I want you to say that your first term is a 1. And then what we're going to solve for is our r. That's what we don't know. Cross multiply. So you're going to get x times 1 minus r equals 1 plus x. Do I want to distribute here? No, I'm going to divide by x here, because we're just trying to get the r by itself. So we'll do 1 minus r equals 1 over x plus 1. Notice how the 1s are going to cancel. So those will cancel. I get a negative r equals 1 over x. So r equals a negative 1 over x. That is my ratio. So what that is going to tell us, if we go ahead and do our series, we definitely have infinity on top. That's what I'm multiplying by over and over and over and over again. So just like over here, I could have, if I want to just do, since I'm multiplying by negative x over and over again, just do a negative x to the end. It's the same thing here. If I start at 0, then my common ratio is a negative 1 over x to the 0 power. That should produce that series. 3, we could go either way now. This is a nice one. If we're using this formula and I want this first term to be a 1, this guy's already set. We already have a 1. This should be 1, which we have, minus, which we have. Our ratio tells us 2x has to be our ratio. So that way we can just look at it and say that r is a 2x. So if I wanted my series, start at 0 to infinity, the 2x is what we're multiplying by over and over and over again. The other way is just set up the equation. 1 over 1 minus r. We know we want our first term to be a 1. Set it equal to the equation that you were given to work with. Cross multiply. The 1s are going to cancel. You would get a negative 2x equals a negative r. We find here as well that our common ratio that we are repeatedly multiplying by is going to be a 2x. Last one, be careful with this. It looks like our first term is a 1, but notice in our denominator, we don't have this written as 1 minus a common ratio. We have a 5 there. So that means we do need to do a little bit of algebra. You might be able to figure that out in your head. Sometimes we try to do that when we have time. It's not necessary. Take the formula. So a sub 1 over 1 minus r. We know we want our first term to be a 1, and we're trying to figure out what our ratio is. So we're going to take this thing, 1 over 1 minus r, and we're going to set it equal to the one that we're given to work with. Cross multiply. So 5 minus x equals 1 minus r. Again, we're solving for r, so I'm going to subtract the 1 over. We get a negative r to equal 4 minus x. So what that would have to mean is r, when we just multiply everything by a negative 1, would be a positive x minus a 4. That's our ratio that we're multiplying by over and over and over again. So if we do our series, infinite from 0 to infinity, our common ratio is x minus 4 to the nth power. All right, so now number 5. It says, using number 4 above, find f of 2. So what that means is this is our function. That's the function that we are writing a series for. So if I use that function, let me not do that here. So f of x is equal to 1 over 1 minus 2x, and I want you to find f of 4.2. We would plug that into our calculator. Here I go again. As I'm plugging this in, I realize I'm being a fool, so hopefully you guys caught that and didn't write all this down. We're supposed to look at number 4. I'm using number 3 right now. Let's try this again. Number 4 is clearly this guy. So you're going to take that as the function. 1 over 5 minus x plug in f of 4.2. That would give us, what, 1 over 5 minus 4.2. Should be a minus sign there. I think hopefully that looks like that. And then 1 divided by 0.8 should equal 1.25. All right. So then what I'm telling you to do now is use your power series found in that problem, number 4, to approximate f of 4.2. So what that means, think about what your series was. The series gives us every single term that we would want. Well, we can't write them all out. If you think back to the problem where we graphed, this little 1 here, it basically shared 1 point with its actual function. It wasn't a great representation of what's going on though. When I did 1 plus x, it was a little bit better. When we started adding all of these terms together, the more accurately it was reflecting what the original graph looked like. So the more and more terms I added in here, it would have given me a more powerful polynomial to use in order to approximate what that curve looks like, what this actual curve would look like. So if we go back to the problem we're dealing with, this is what this is basically having you look at. If I just use the first term, so let this be a 0, so x minus 4, this is going to be our 0. Our first term is a 1. So we're already reasonably close here. But what we know is if I add more terms here, it more accurately reflects what this graph looks like versus just 1 and only 1 term. So if I do another term, fn is a 1, I would get x minus a 4. And again, we said the more and more of these we add, the more accurately the polynomial will approximate this actual function. So the more of these we put in here, the more accurately our approximation is going to be, and the closer it should be getting to 1.25. When we do these, we're going to do these more on the next lesson. I will tell you exactly how many that you're going to use. It'll usually tell you how many you're going to do. Let's say we stop at 3. So the way we would now write this, there's a couple of different things we can do, and this absolutely is something we want to understand AP test-wise. This is an approximation. This is one of the things they will force you to use the approximation symbol for. So this is an approximation for our function. So if we use f of x notation, we would want to use that approximation symbol. Or, make this a little bigger, or you can see a little more. We could also say that this is p, and then we would put sub 3 of x. This is a polynomial, so we're using a polynomial term, and our subscript corresponds to the degree that we stopped at. So it's called a third degree polynomial. Since we're doing this as a polynomial, we would go ahead and use an equal sign, because this is going to be the actual value of our polynomial, and we would then know that's the approximation at 4.2. So then what we would do is take either one of those, so whichever one you prefer. This would initially get written the exact same way. So whichever you prefer now, if you prefer the function notation, or if you prefer our new polynomial notation, take either one of those. I'm going to use the function notation, and I'm going to say f of 4.2 is approximately, if you use this guy, you would just write the third degree polynomial value for 4.2 would equal whatever, and you're going to get the same values here and here, but now we go ahead and find those. So this would be 1 plus, let your x be 4.2, so this would be 4.2 minus 4, so 0.2. If I plug in a 4.2 here, I get 0.2 again, now that's squared. If I plug in 0.42 or 4.2 there, I'm going to get 0.2 cubed. If we now evaluate that, what we will get, we get, turn them right here back on here, 1.248, which is very, very, very close to the actual value we got up here. Also understand, the more terms that we used, the more accurately, sorry about that, the more accurately it's going to give us our value. So if we would have used this first one, 1 is pretty close to 1.25. But if we added this 0.2, now we would have been at 1.2. So now we're even closer. Let me write it down here. Here's the real value, 1.25. This was our approximation using the third degree. So very, very close. If we just use the first term, pretty close. If we added the first two together, we get closer. If we add the next term together, this here, we get 0.04. So now we're 1.24. If we add this next term together, the 0.2 cubed, let me make sure so I don't screw this up. Yeah, 0.008. We add that to our 1.24, and then that's what is going to give us that 1.248. So we were getting closer and closer and closer to the real value with the more and more terms that we add. So if we were to continue this process, we would get closer and closer to that real value. So being able to use a power series to approximate values is basically what we want to walk away from here knowing. What we do on Tuesday, so this is going to be a little shorter, it would appear. What we do on Tuesday is there's a couple special types of series that we dive into, and I think it's just better to treat that as just one full day, and that's what we'll do next week. So that's pretty much a wrap for this one. Hopefully that made some sense. Hope everybody has a good weekend, and we'll see you next week.